we will I had asked you, I mean this was a 2-dimensional problem which I wanted you to discretize, and we took 1/8 of the symmetry. So, this is the why this is not coming on the screen. No. So, this is the problem that we took it, and then we discretized this small 1/8 because of symmetry, and into 4 elements, and then I told you these are the coordinates of various nodes, and you have to find out the K matrix and F matrix for each of the elements. So, how many have you done? Okay. So, you please very good. If you have done it, it is very nice. So, you just compare with whatever is my result, that is K, for example, here element number 1, which is confined by node 1, 2 and 3. Element 1 is, so you have to also say that what are the nodes, in what order you are putting the numbers. See, global numbers and local numbers. So, 1, 2, 3 of element number, these are the global numbers that we always give. Then we can start from any node number and move in anti-clockwise direction. But then you have to say which is your local numbers 1, 2, 3. So, for example, element number 1 element that is K we have taken of 1. I will put a superscript on the top, means 1. Here we have taken 1, 2, 3. The order is same as 1, 2, 3, 1, 2, 3. We could have taken also 2, 3, 1, 3, 1, 2, that also is possible. You can start from anywhere, because what is your local number that you are prescribing. So, we are saying yes, element number 1 is reckoned as 1, 2, 3, and then the stiffness matrix of this, then if you put the same thing also for element number 2, 2, 4, 5, but if you put it like this only 2, 4, 5, if you change it, then it will not be 2, 4, 5, and another one is K 4, 3, 5, 6. If you number the nodes of these 3 elements like this, then the stiffness or the K property, it will be 3 by 3 matrix, and it comes out to be 1, minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 1. Now, you please tell me whether anyone has got this. Unless you try, how will you get it? There is some mistake. So, you please check your mistake, and this is the K property. Now, element number 3, no mistake, you cannot afford to make mistakes, because mistake means the whole thing will go. K? What is K 1?
K values.
So these are the K values. This is the 3 by 3 for element number 1. It is.
So K is prescribed here 2. For this problem, K is 2.
K is 2. Yes. K is 2. No. K equal to 2. That coefficient conductivity is 2. 2. Okay. Then, 3. Element number 3 is 1, 2, 3 is 3. 3, 2, 5 I have taken. I have taken 3, 2, 5. I have taken in this order. This one, this is my first node 3, then 2 and then 5. Okay. You can take again any one. This has been taken like this and then it comes out to minus 1, minus 1, minus 1, 1, 0, minus 0, 1. Then f. F is of course very simple. F is, there is no problem. F will be again f, f or p. In our case it is p because there is no other term. So, it is p. So, p for 1, p for 2, p for 3 and p for 4. Every, because this problem anyway is only for illustration. So, it comes out to be the same. If you follow the, it comes out, it is 2.5, yes, 2.4, 2.5, 1, 1, 1. Node numbers are already prescribed, it is. So, at each node the concentrated force or concentrated contribution of the non-homogeneous term is 2.5 at each node. That is. So, this is all. First job of any problem is to find out the element property. So, these are all the element property. And then once you have got the element property, next one is you have to find out the total k by summing up, and then you have to find out the total p again by summing up. Here E is going to 1 to 4, 1 to 4. So, this job has to be, this is you have to do. Next job is, after having obtained the element property, you have to find out the global. Now, here I will tell you about the assembly. Now, the total number of nodes in the problem, they are 6 in numbers. They are 6 and so I would like to keep it 6 rows and 6 column. So, I will write, because all these element properties will be written in the form of 6 by 6, not 3 by 3. So, I will just take 1, 2, 3, 3, 4, 6, 1, 2, 3, 4, 5, 6. Let us say, so how will it be? So, this will be your, whatever will come here will be your k multiplied by phi 1, phi 2. This, that equal to, of course, the load, that I will write on the next page. So, let us first assemble the, that equal to the total right hand side, that is P. So, how will you, now element 1, you also has to, element 1 is 1, 2, 3. So, that means they will be confined in this 3 by 3, left hand 3 by 3. So, I will write it if it is 1, because 1 2 3 there is no confusion. So, it is 1 2 3. So, I will write it notionally first. Notionally means in terms of k 1 1 k 1 2, as if these matrices are, these element matrices are in the form of k 1 1 k 1 2 k 1 3 of element 1. So, let me write down. So, this is will be k 1 1 1 k 1 2 1 k 1 3 1 3 3, rest all 0. First element has been written in the form of 6 by 6 matrix with all the rest of the elements 0. So, this is K matrix in expanded form. Now, the 2 is 2 4 5, the order is 2 4 5 is 2. So, first one is 2, next one is 4, next one is 5. So, how will it be? So, 2 will be 2 4. So, remember this order. See, 1 is 1, 1 2 3, 2 is 4 2 4 5, 2 4 5. That means, the elements will be sitting on second, fourth and fifth rows and same columns. So, you have to have, that means, second row is here, this is the second, So, that means, starting from here 2, 4 will be the next one is here, next is this location 2 4. I mean, this is okay, next element is here, but then this is the diagonal element, and 5 is, this is the fifth. So, these are my 4 rows 2. So, next one is 2 4 5. So, it will be k 1 1 2. So, k 1 1 here, k 1 1 of 2 here 2. Are you following? Yes. Then 4. Now, k 1 2 of 2 will go where? 4. So, k 1 2 of 2 and k 1 3. Yes, 4 1 3 of 2. Okay. So, first row is complete, second will be now 2 4, fourth will be here, here it will be k 2 1, 4 k 2 2 of 2 and here k 2 3 of 2 and 5 is here. See, this is called direct stiffness method, in our structural mechanics jargon. That means, we are assembling the stiffnesses of the individual elements and putting it in the global. So, size now is of global, but then these are coming from the contributions are coming from the elements, but they are putting properly at the proper place. So, I think we have done the right thing. I think fifth row is k 3 1 2, then k 3 2 and then fourth and fifth will be k 3 3 2. This is this one will be k 3 3 2. Yes, that is right. Thank you. Next is third element. Now, third element is element number 3. Element number 3 is, we have numbered as 3 to 5. 3 to 5, yes. So, now here is the real 3, third row is here. 2, second row is here and fifth row is here. So, here only people make mistake. It is not coming from 2, 3, 4 or something, the first. So, k 2, 3, 3, 2, 5. So, 3, 2, 5. So, at the third one 3, 2, 5. So, third one. So, wherever it is cutting. So, this is my diagonal 3, this is my. So, it will be here k 1 1 3. Then on the you stay on the same row, you stay on the same row 3, 2, 5, 3, 2, 5. So, here it will be plus k 1 2 of 3 and fifth one is here k 1 3 of 3. I hope k 1 1. So, this is 3 k 1 2 of and in the third row k 1 1 of 3, okay, k 1 anyway that is a mistake, the small mistake does not matter, and k 1 3 of 3, yes, it is correct. Now, 3 2, then you go to second row is your second row is actually I mean it happens to be second row here also. So, now we go to the, but then this is my 3 2 5 it is. The numbering is from 3 to 5, that means first column is 3, second column is 2 and third column is 5. This is what it should be kept in mind. So, then here it will be here k 2 1, then here k 2 2 3 and 5 na. So, k 2 3 3, k 2 3 3, fifth one 2 3 3, this is okay 2 1 3 and then k 2 2 3, yes, it is right. Then you go to fifth row. Fifth row is here, but then the numbering is 3 2 5. So, this is the first column is 3, then 2 and then 5. So, here it will be k 3 1 3 plus 3 2 3 and 5 plus k 3 3 3. The k 3 3 3 is okay, then k 3 1 and the third one, fifth one k 3 1 3 is okay, k 3 2 3 is okay. Yes. So, this is how we have filled up the third. Please do 100 times this exercise of assembly, then only you will master. It is not because you don't be dependent on computer program which have already been written and running, that does everything. But then how that computer program was developed, in fact, you also write a simple assembly program. You write an assembly program based upon what they are all available now. Codes are available, they are in books. So, you please write and do this manually at least 100 times. Take different and then different node number, different configuration and then do it, then only you can. Then last element is fourth element, 4 is 3 4 6. So, fourth 3 5 6. So, 3 5 6. So, 3 5 and then 6 so far has been blank 3 5 6. So, first row is 3. So, row is here 3. So, we are here at 3. So, this one will be k 1 1 4. Yes, please. Then 3 5. Move on the same row. You be on the same row. 5. So, it will be k 1 2 4 and 6 is same row. So, it is k 1 3 sorry 4 k 1 3 4. Okay. I think this is okay. 4 I have written, yes, first row. Then fifth row is here and order is 3 5 6 3 5 6 is here. So, third one will be plus k 2 1 4 k 2 1 4, second row first column, fourth element of third. Then you go to the fifth place is here 3 5 plus what? Is it okay? I am making a mistake. No 3 5 6 na. So, where is the third row?
So, at 5 5 will be having k 2 4.
No, but then how did I write this here? Third one. This is correct. Acha, this one is okay. Acha, fourth one, 3 I have written correct. This one is written third. 3 is okay. 3, then 5 also I have written 4. This is okay. First row is, third row is over. Then you have to go to fifth row, but then the locations are third column, fifth column and sixth column. So, third column, fifth one. So, here k 2 1 4 is correct. Then fifth one is k 2 2 4 and then the sixth one k 2 3 4. I think this one. Okay. Then I think one more row is remaining, sixth one third. So, here at third place. So, k 3 1 4 5 fifth place k 3 2 4 and sixth place k 3 3 4. Yes, this is right. Now, I can fill up all. Let me see which are the other 0 ones. So, first row there should be 1 2, first column 3 zeros, okay. Here it is okay, 1 1 2 3 k 3 2 3 2 1 1 2. Then this is 2 1. This is 2 1 is 2 correct. 3 1 3 2. Then 1 0 here. This one everything is filled up 1 3 1 2 3 1 2. This is okay now. These subscripts are 2 1, not 1 2, because I have a no, this is 2 1. I mean second row first column. That is so that should be written, because you do not make mistake of, because k 1 2 is equal to k 2 1, that does not mean that you use any subscript, no, because then it will be confusing. So, please use this. Then here addition of 3, then there is a 0 here, then this and this. Now, come to the fourth one, there is 0 here, k 1 2 again 0 here, k 2 2 2, k 3 2, k, then 2 2 is okay, k 3 2 is okay, then there is 0 here, and here 1 3, no, before this is 0, 1 3 2 3, 1 3 1 2 4 correct, 2 3 is okay, 3 3 3 3 3 3 3, this one 2 4 okay, and last one there is 0 here, there is 0 here, k 1 3, again a 0 here, k 2 3 4, that is okay. Yes. So, this is what is the assembled k equal to phi is written already. Now, f right hand side will be right hand side. Right hand side will be 6 by. So, you can just see it is only a 6 by 1. So, first one is what? 1, 2, 3. 1, 2, 3. 1, 2, 3 means the first one will be f 1 of 1, I mean sorry p 1, let us call this p 1 of 1, then p 2 of 1, then p 3 of 1, rest all 0. First element is because it is 1, 2, 3. Second element is 2, 4, 5. 2, 4, 5. So, 2 is here. So, plus p 1 of 2, 2, 4. 2, 4, third one 4 is here, p 2 of 2 and 5 is here. 2, 4, 5, 2, 4, 5, sixth one is here. There are third one is 3, 2, 5. So, third one is 3, 2, 5. So, plus p 1 of 3, then 2. I will write it p 2 of 3 and 5 is here, plus p 3 of 3, and last one is 3, 5, 6. So, 3 is first, third 1, third. So, it is p 1 of 4, 3, 5 is here, plus p 2 of 4 plus p 3 of 4. So, 3, 3, 2, 3, 2, 4, 2, 3, 1, 1, 3, 1, 4, 2, 1, 1, 2, 2, 3. Yes, this is right. So, this is, so this, that means from this side it comes to equal to your this. And now, since you have already got these numbers are already got, you see here you have got these numbers. So, this, so you have to just substitute. So, this is the advantage. So, once you have this, you please substitute, and after you substitute, so you get here 1 minus 1 0 0 0 0 minus 1 4 minus 2 minus 1 0 0. I have done this. So, minus 2 4 0 minus 2 0 0 minus 1 0 2 minus 1 0 0 0 minus 2 minus 1. These signs are okay now, minus 1, just check up, because once I had made a mistake. So, I have corrected, but I do not know. So, then 0 0 0 0 minus 1 1, this multiplied by 5 1 5 2 5 3 5 4 5 5 5 6 equals F1 2.5, how much? 2.5, 7.5. This is 7.5, 3. There are 3 additions. and again 7.5, then 7.5 and 2.5. See here, what is to be noted is we are given in this problem that 5, 4, 5, 5, sorry, this one is 6, 5, 6, 4, 5, 6 are 0. 4, 5, 6 are 0. So, 4, 5, 6 are 0, that is all right, but then whatever nodal force that will go to that, it will not affect, because it is like support. Supposing you have a beam and displacement here is 0 and you also put a load. Will it deform the beam, that load? No, it is not, it is directly going to the support reaction, but reaction it will be reflected. It will, yes, in the reaction when you find out, then it should come from the. So, if the support is constrained, there is no displacement and the nodal force is there at the support, it is not contributing to the deformation. Okay. But then the reaction will come. So, we also have, so wherever support, wherever you have your values are prescribed, dependent values are prescribed, you should think in terms of reaction and constraint. That means, W is 0 and then there is a shear force. So, either W is prescribed or shear force is prescribed. Either the load is there, yes, you can always solve a problem with a cantilever with a load, then this will be deflect, there is no problem, that is applied to the node. But if that node happens to be constrained, there is no, if you put a support there, so then that load will directly go to the support and there must be, you must get the proper reaction. So, wherever values, wherever you have dependent variable prescribed, there must be reaction. So, we always say that on these there must be reaction here. So, that means, here there is something hidden, reaction 4, reaction 5 and reaction 6. So, that is a part of, if it is prescribed, then there must be reaction. So, okay, now this needs to be solved. So, there is no problem. So, put 5 4 5 5 5 6 equal to 0. Equal to 0 in this, and you will get only a 3 by 3 matrix that need to be solved for your, and that will be 1 minus 1 0 minus 1 4 minus 2 0 minus 2 4 multiplied by 5 1 5 2 5 3 equal to the right hand side, that is 2.5 7.5 7.5. Because this one, if these are 0, so all this will always come. So, this multiplied by this submatrix, this one into this one into this one into this, these will always be 0 equal to this. Is it okay? So, this one should give us this set of first part should give us phi. Please find out. Now, second one, you can use Gaussian elimination. Of course, 3 by 3 is very simple. If you multiply this by 2, you can introduce a 0 here by multiplying by 2, 4, 8 equal to 15, and then add this. So, you will get a 0. So, you can get a last one 5, 3. So, please solve this, and if you solve this, what you get is the following. So, you get 5, 3, because you always get from the in Gaussian elimination from the last one. 5, 3 comes out to be 5.3123. 5, 2 will be coming to 6.8748, and 5, 1 9.3748. Then I had told you total heat in after all Q is some kind of heat input to the system. Q, I mean sorry, F that is F that we are prescribing, F is total heat input to the system. It is a non-homogeneous term. So, the total heat input will be F times the area, total area of the plate. That will be the total heat, because that is per unit area, that F. So, now you have got, so you think like this, total load applied to the system, you must get the reaction. The reaction and the applied load must balance each other. So, this is you have to take the structural mechanics concept even for solving thermal problems. So, whatever heat is input from the, and which are the nodes which are constrained in this one, the last 3 nodes. So, that means whatever reactions you get, it must balance the total heat input. So, you find that R 1 R 2, that is R 6 comes out to be minus 2.5, R 5 will come out to be minus 18.124, and R 4 comes out to be 9.3748. These are the reactions. Now, addition of all this comes out to be, I do not know, this is 8 at 8, Sadono, 36, is 29, 29. This is 29, and if you say, if you take F1, F, what is the value of F? F times the area is how much? What is F in this problem? 2 or 2.5? I mean F means, sorry, P, I mean F, I am talking of P, I am talking of P, P is 2.4, and area is how much? 2.4, area is how much? That is only 1/8. 1/8 is how much area? 12.5, yes, ठीक है, because this is 5 into yes by 2, triangle, area of the triangle, yes, 5 into 5 by 2. So, 5 into 5 by, and this area, so this also, this will come out to be how much? This is 30. Okay, there is slight. So, this should match this one, this P times area must match this reaction, because those are the only three points or 3 nodes that are constrained. So, it must be whatever we have applied to the plate must be the reaction. I mean, I am just giving you, this is just a check. So, this is a check. Incidentally, this problem has exact solution. It has exact solution, this problem. It has been taken from exact solution means it has been solved analytically, no numerical, it has analytical solution, and analytical solution is this one is 5.3125, this one is 6.875, and this one is 9.375. So, you can just see how much is the difference, because this you have done numerical by taking 4 element discretization, and this is the analytical solution. That same thing, the reactions are exact reactions are minus 2.5. You please compute everything yourself and check. 8.125, 18.125, this is 18.124, and this is 9.375, 37.
By solving directly without Gauss elimination,
Yes,
we
yes.
are getting the
We are getting 9.375 that fiber.
N-
500
Acha.
values
that
are
comes out to be 9.375 only.
Okay, very good. I don't know. Then sometimes some errors creep in, in a numerical process, because you are doing not. So it was a good approximation of the entire, I mean what I want to say, and so this is how. But then here it is, as you see that example means hard work, you have to solve. While theory I can give a lecture and then it will look everything very fine, but in example you are likely to make and that practice only will make you perfect. So, please solve some problems of 1 dimension and 2 dimension, take some problems from your book. There are problems given in the book, you please take the same problem, I think answers also are given. So, try at least couple of problems, that will make you. So, this is how now we have taken a simple triangular element, and ultimately you have to write down a program which as a student we had done, as a part of this course. Now, I am not insisting, and there are because it is after all it's left to you. If you don't do it, you will suffer later, I mean you will have difficulty later. So, after so many years of experience, so the program is structured, just to give you, I mean I will just display this, it will look something like this. I do not want to, if you have a normally any finite element program will always have a first there will be one subroutine wherein all the data will be input. We will input all the data, means geometrical, material, node number, coordinates, all these things have to be properly read. This is I am talking of a research program or for understanding, not for commercial program. So, then you should again have here a element property, although I have written here Steve, but the element property. What is element property? Yes, you should compute, there should be one program wherein you should define your elemental properties, that means K and F element. So, computes element is difference and nodal loads are element property. I will now say element properties. Then we also write another program which will assemble these element wise. After having read this element wise, because this will be computed element wise. Now, for each element we have computed, then we have to assemble. So, there also we write a simple program, assembly program, addition program, how these have to be added. Having done this, then you have to introduce the boundary condition, which I have not given here. You should before this you should write a introduction of boundary condition over here. After assembly, there must be boundary conditions, introductions, because unless you introduce the boundary conditions, you cannot do Gaussian elimination. This one is Gaussian elimination or Gaussian reduction. That will be done only for after you have introduced the boundary condition. Okay. Then you do the back substitution, then you compute your quantities, evaluates the stresses or whatever it is, you have the something else is there, that also. Basically, you compute in all this block, all the 3 blocks below, it is the output. What are the quantities you have? And this is how it works, a simple program. So, a structure of program is always like this. Now, actually you must write. I mean, I advise each one of you, you please practice. If you want, I can give you a sample program which you can study and then build upon that. I have got a one. So, that you can take it from me, I will give it to you. But you please write a program, run it, have some practice, because then only you will understand the intricacies. In our time, these programs were not available, that is ready made like ANSYS, then Abacus, then SAP 90, all these programs came much later. So, they were also developed after all by the students only, all the university students, when they went out and they found that yes, there is a lot of repetition. It is the same program, because once you have written a good assembly program, it will work for any stiffness, any force. It is not that it will. So people started, they felt the need, that this is very standard procedure, and why not make money out of it. So, that is how number of companies came, and they started selling these as software codes. Otherwise, most of the work initially from 1965 onwards up to 75, they were all done in the universities. But the same students, when they went out in the market, they they established their own and the one professor who has become very famous in this, and of course, besides that he has maintained his academic stature, is Bathe, because Bathe did his PhD from University of Berkeley, K.J. Bathe, under Wilson, and he finished his PhD and joined MIT as professor. So, he continued, but at the same time he also opened a company outside, which is run by some of his associates. So, whatever is done in the university, it is passed on to that company. Okay. So, that way he has maintained his academic stature as well as his business interests also. So, he is a very rich man. So, he because his software is Adina, 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 that sells. So, that one. So, that is how it goes on. Okay. All right. So, this is now. So, I have given you. I would like to review today. So, we have done now fair amount of work, and so BVP is over now, more or less. Boundary value problems, and we have learned both FD and FEM and finite element, FDM and finite element for boundary value problem. We have also had a glimpse of 1D as well as 2D problems for both these. Then for initial value problem, yes, we have done already FD, and we have learnt about what is called explicit methods. We have also learnt about what is called implicit, because here you have to develop what is called time stepping scheme to march in time domain. You are marching in time domain from initial stage. At initial stage, at 0 datum, your conditions are given, and then from there on you have to go in time. So, you have to implicit. So, finite difference, this one is we have done, and we again here we covered both 1D, but not 2D. Did we? I told you how to. I told you. So, 1D and simple 2D problem, because 3D just extension of 2D. If you have done 2D, then 3D you can always. So, 1 and 2D you must do, at least simple problems. Now, we can follow another approach. Yes, finite element here for IVP. Finite element. What do you mean by finite element? Finite element, because here we have used finite difference both in space and time. By following this, we have used here. Now I am saying we have just now learnt here finite element for space, for solving boundary value without time. Just now we have completed. So, what we will do, whatever we have learnt, we will make use of this for solving time dependent problem. So, I will take first here 1D and try to explain to you how to. So, now you say that now our problem, that is phi vector dependent variable, is a function of x and t, is a time. And what is the example of this is our first order transient problem, which you have already seen. For example, del phi by del t equal to k times del square phi by del x square plus p x. It can be t also, I mean it can be function of t also, it can be anything p x t. So, this is the heat equation, transient heat equation. Now, there are two dimensions involved, x and t, and earlier what we had taken a xi point here and Tn here, and then we took a general point here. My p point had a coordinate xi Tn in time and space, and we discretized both simultaneously, time dimension as well as x dimension simultaneously by finite differences. Are you with me or not? We discretize both x as well as time, because that is how I am able to write. I am writing at a point. So, it is Tn. So, we will now slightly change our approach. Should we discretize both simultaneously? Should both x and t be discretized simultaneously? Obviously not. And we saw it also. I think I have also shown you that it is not necessary to discretize both simultaneously. I will discretize, I will write only at x I my equation and let my t be continuous function. I will not write at T n, and then we got a ordinary differential equation in T. And I told you that is another approach for solving, because there you can use now your ODEs, how to initial value problem. ODEs are there, and I told you to read ODE chapter completely, that you can understand. There is nothing that you cannot follow there. So now what we will do, we will follow the same approach. Only thing is space discretization by finite element. So, we will go in steps and we will discretize space x only. We will discretize space only by f d finite f e. So, how will we do it? One is, yes, one thing comes in our in all these weighted residual. So, first we say always that phi is approximated to phi hat. Let phi hat x t be as sigma nix Reed's method, except that here earlier we were saying ni phi I. Phi I was becoming nodal value directly. So, here again it will remain nodal value, but each nodal value will be a function of time. So, it is I ok. So, I going from 1 to n, any number of nodes are possible. So, this is Reed's. And then the rest is all standard. There is nothing new. We have already learnt. This is the crux, partial. So, this is called partial discretization. We are discretizing because we are using shape function only for x. We are discretizing, we are keeping t intact, and they are all hanging with all the nodal values x. So, once it is there, then your error residue will be what? I mean, it will be like this only, na? K times I will put this also in the, yes, this is my residue. Residue will be, if you substitute phi hat in the differential equation, and therefore, your weighted residual W R M, W R is statement. I also call it weighted residual statement. And strong. Will simply be integral from x 1 for the domain x 1 to x 2 w times this k del square phi hat plus p minus c and this we will still keep and this must be set equal to 0. So, this is all is a change. The change is very minimal. I think we have already handled this part. This term we have already handled. This term of this integral we have already handled. Now, the only thing is this is a new term. This is new. Weight times c times d phi by dt integral over dx. How it will look like? All other parts are as before. How will it look like? Can you say this? Huh? First of all, we have to convert into weeks. That is I am saying handle means yes. I mean this is strong. So, this anyway by integration by parts you do. This is as it is, and this is also there is only first derivative and that too with respect to time. So, it will remain as it is, but then we have to substitute this. If you substitute this here, see if you substitute this form here, see there is no derivative with respect to x. So, only this will become, that means all the nodal quantity will become derivative, only d phi I by dt, only this part will get differentiated with respect to, and then this will remain as it is once we substitute this over here. So, we will get, so I will just write that statement. So, it will be your boundary term, I mean 0 will be equal to weight times k times d phi by dx. One term is like this and that is to be evaluated at the boundary x 1 x 2 minus integral. I am taking the weak form please, directly I am taking the weak form, I think you all know. So, weak form will be, the first term will be dw by dx k x plus w times c, this one I am talking of this c, times c del phi hat by del t, and this I will say this will be yes, these are the only two. Any other term, what happened to our load term? So that also should be there. So, plus p time w into integral plus w into p. P is there na? Yes, p x t is there. So, this also. So, all these 3 no, this one is, if I am not right, I think everything is under integral. So, this is this. This is the weak form. This is the weak form of this. Yes, this is giving me this. This one I have kept. There is a minus sign, I think somewhere. Yes. this one C, this one will be minus, inside it is minus, yes, inside minus, no, inside plus,
WP का minus
minus WP का minus होगा, yes, you are right, this will remain plus and this one will become minus, if you are, so this is okay. Is it okay? Have you understood? And then next is, so these two you have already done, this and this we have already done. The only thing is we have to deal with this. So, what will be the form of this? The form of this will be, so I will write here only boundary term minus integral I will use n1 dash. N1 dash means derivative with respect to x. N1 dash phi 1 t. Let me write down t here, plus n2 dash phi 2 t, etc. 1 integral I will keep it separately, plus integral n this w minus integral this one w c. So, it is w c times and d phi by dt. So, it will be n 1 phi 1. Now, I will write here phi 1 dot. Phi 1 dot means derivative with respect to time, plus n 2 so that one you have to have a bracket. So, let us keep this bracket is square bracket, then this is square bracket closes, and then let us say this is this and this is dx. It will be something like this, and rest is okay. You please write down for any jth and j. Then you write down this equation at number of nodes. This is a general one at any point, at any space point. Weight can be anything. So, now I am saying that yes, this equation can be written as many number of points as possible. So, we will get a system of algebraic equation, and the only thing is that this one will give you a new, because if this one is there, first one is n j. So, what you will get n j n 1 first line, this will be n j for any w equal to n j, then j equal to 1. So, it will be n 1 n 1, n 1 n 2 etcetera. Now, those are not those are the only ones which are functions of x. This is not function of x, phi dot t. So, that means I can integrate those quantities, each one. that means n1 n1 times dx n1 c times dx I can integrate from whatever integral is there. Then this can be taken outside the integral. This quantity is independent of x, this quantity is independent of x. I can take it outside. So, in this process, just like we were getting a K matrix here, a P matrix here, we will also get another matrix here, and that matrix we call a capital C matrix, capacitance matrix. So, now we will be dealing with K matrix, P matrix and C matrix, and the form of these three will be. So, then I will stop. So, we will have equal to 0 will be equal to. So, boundary term. So, there will be B t is 0 minus this one will be size can be anything. Now, here it will be what will be the so this will be K matrix minus plus this will be second minus third one I will come C matrix, and only change will be instead of this it will be phi 1 dot, phi 2 dot, like this. So, general I going j going from 1 to n, I going from 1 to n, there are n nodes in the problem and I have to write down all the equation at all the n points. So, this one also is going from 1 to n and then this j also is going to. So, I will have j equation, therefore, all will be square matrices and then it will be like this. So, k everything else is defined except C. So, each term of C I j will look like what? N I is okay, N I is a function of x by the way, times small c times n j, because there is no derivative here. Here the derivative has gone into this with time. So, it has this has become nodal point itself has become a derivative. So, here there is no derivative here times dx. So, every coefficient of C, all k and p etcetera that you already know. So, this is the only new term that has come here. So, your C matrix will look like this. Okay, so we will stop here, and I will only say that yes, this we can write just to, because mine is never ending. So, this will be a C matrix, supposing this we call is a D. If you call this as a D matrix phi 1, phi 2 etcetera to phi n, and D itself is a function of t now. So, each one is a function of t. Each nodal quantity is a function of t. So, then this will become what? This will become d dot. This will become d dot. So, you will get a matrix C d dot. I am just telling you minus minus both are minus. So, let us take positive k d, this will be d k d plus I will call this p, let it be on this side only. No, but this is minus as per our convention does not matter, let it be minus p, and minus p and plus boundary term in case it is there equal to 0. This can be combined into f. These two are combined into f. So, you have one additional term because of this derivative with respect to time. Okay, thank you. Close it.